I welcome you to the second part of our discussion on kinematics of fluid flows, and I would like to briefly recapitulate what has been covered till now in the discussion made by Professor Som. So, the kinematic description of fluid flow, the Eulerian and Lagrangian description, different types of flow, acceleration of fluid flow, as well as deformation of flow in terms of angular deformation and linear deformation. So, we will go ahead with that, and I will take it over from where the previous lecture was concluded. So, we will briefly try to recapitulate on the volumetric deformation, because volumetric deformation has a very important sense associated with it, which is the compressibility of fluid flow. So, the volumetric deformation was defined as change in volume per unit volume per unit time. This is rate of volumetric strain. Rate of volumetric strain was derived. I am not going through the derivation anymore because this derivation was already done. Which is the divergence of the velocity vector. So, if the divergence of a velocity vector is 0, then what does it mean? If the divergence of the velocity vector is 0, then what does it mean? It means that there is no change in volume of a fluid element. If there is no change in volume of a fluid element, that means that the flow is incompressible. So, incompressible flow or incompressibility of a flow follows from a basic kinematic constraint that there is no rate of change of volume per unit time. So, incompressible flow by definition should satisfy the divergence of the velocity vector equal to 0. In this sense, I would like to emphasize that there is a subtle distinction between the two terminologies, incompressible flow and incompressible fluid. Like, we will come into this later on in more details, but by the term incompressibility of a fluid or compressibility of a fluid, we are essentially trying to see the sensitivity of pressure with density, or sensitivity with respect to change in density with change in pressure. So, if there is a sensitivity of that kind, that there is a significant change in density because of change in pressure, then we say that the fluid is a compressible fluid. So, the paradigm of incompressible flow is basically a kinematic constraint that there is no change in volume of a fluid element. For an incompressible fluid or a compressible fluid, we are essentially asking a question that is the density a significant function of pressure. If the density is a significant function of pressure, then obviously it is a compressible fluid, otherwise it is an incompressible fluid. So, these are subtle distinctions. These distinctions are not technically that much of important except for certain special situations which we will discuss later on. Now, this equation, this condition of incompressible flow can be also conceived from several other considerations, And one of the very important considerations, which is of course not directly a kinematic consideration, but is a follow up of the kinematic, several kinematic considerations, is the conservation of mass for fluid element. Conservation of mass. This is a very important topic in fluid mechanics and one of the most fundamental considerations, and as teachers I think this is one of the very important topics that you should discuss very carefully with all your students. So I mean there are several ways of deriving the conditions or deriving the equations describing conservation of mass, and I would encourage you to go through as many types of derivations as possible. In this particular discussion I will discuss about a couple of derivations. There will be some additional ways of deriving this which will be derived by Professor Som when we will be discussing about the Reynolds transport theorem. So there are several ways of looking into these conservation laws, and there are, and actually more and more number of ways in which you look into these equations, you will gain more and more insight into this. So now what does conservation of mass physically mean to us? It means that mass is conserved. Now let us start from that. Let us write the mass. Mass is equal to density into volume, right? None of us will argue with this. So then what we do is, I mean here we just follow an approach which is based on the total derivative of both sides. So when we say the total derivative, the capital d dt, it includes two possibilities. One is the change with respect to time at a fixed position, the other is the change due to the change in position and encountering a new velocity field at a new position. So these two effects combined together can give rise to a change which we reflect in terms of the total derivative. To do that, what we do for purely for manipulation, what we do, we take log of both sides. So ln m is equal to ln rho plus ln v. Just take log of both sides and then take total derivative of both sides. So 1 by m dm dt is equal to 1 by rho d rho dt plus 1 by v dv dt. Okay. This is a very simple equation, but it is a physically very meaningful equation. So we will start looking into various terms in this equation. What is this? This must be 0 because by definition of conservation of mass, mass is conserved. So there is no total derivative of the mass. So this must be 0. Come to this term. What is this? Let us see what we have written here at the top. Change in volume per unit volume per unit time, that expressed in a differential form is this one, right? So this is nothing but the divergence of the velocity vector. We can simplify this or open this equation up so that we multiply both the terms in the right hand side by rho, so that we get 0 is equal to So can you now tell that what is the simplified form of this equation if the flow is incompressible? If the flow is incompressible, then divergence of the velocity vector is 0, right? So if the flow is incompressible, then incompressible flow will lead to total derivative of density equal to 0. This does not necessarily mean that density equal to constant. So this is a very, very important misconception that sometimes we try to adhere to when we transmit this to our students, that assuming incompressible flow, rho is constant. This is totally wrong. Rho equal to constant is a special case of incompressible flow, but there are possibilities in which the flow is incompressible even if rho is variable. I will show you how. So let us move ahead with this. So what is our condition for incompressibility? Condition for incompressibility is d rho dt equal to 0. So let us expand the total derivative and write okay. So this is the condition for, this is a corollary of the condition for incompressibility in the flow. So for, always remember, the basic definition of incompressible flow is in terms of a kinematic parameter, divergence of the velocity is 0 and nothing else. And this follows from that kinematic constraint. If you put that kinematic constraint, if you substitute that kinematic constraint in the equation of conservation of mass, this is what it leads to. Now does this equation mean that rho is a constant? If rho is a constant, this equation will be satisfied, there is no doubt about it. So rho equal to constant is a special case, but it might so happen that rho is not a constant, but this term is there and these terms are there, and let us say this term and this term, these are exactly same in magnitude and opposite in sign, so that sum total is 0. That is possible. So it is possible that density is varying, but it is incompressible flow. This is known as variable density incompressible flow. I will give you a physical example. Many times we talk in terms of mathematics and it is not possible to perceive it from a physical point of view. So let us take a physical point of view. Let us say that there is a fluid in a control volume which is changing its phase. Okay. So let us say it is transforming from liquid to vapor or solid to liquid. Solid to liquid is of course not totally in fluid phase, but liquid to vapor is totally in fluid phase. So when it is changing in a control volume from liquid to vapor, let us say it is expanding. So at a given location, the density is decreasing with respect to time. So this is negative. This is compensated by this advection term which is positive. So that must be compensated by some transport across the faces of the control volume, so that this net term is 0. That means that you have rho at a given location changing with time, but still it is acting like an incompressible flow. So there are situations when the phase change may act as a compressible flow. It all depends. So what the example I have given is it doesn't ensure that it is incompressible flow. It will ensure it is incompressible flow only when these two terms exactly balance each other. When these two terms do not balance each other, then that flow becomes a compressible flow. Okay. So we will go ahead with our discussion on the conservation of mass. So the equation that we derived, we will go ahead with that, considering that it's a general flow, it may be both compressible as well as incompressible. So we will expand the terms. So this is the first term. Let us write the second term maybe with a different color, plus rho okay. So we can combine terms, we can combine u del rho del x with rho del u del x, so that becomes del x of rho u. Okay. We can similarly combine these two terms, rho del v del y and v del rho del y, so that it becomes del y of rho v. And similarly we can combine these two terms, so it becomes w del rho del z plus rho del w del z, that means del z of rho w. So it becomes 0 is equal to del rho del t plus del x of rho u plus del y of rho v plus del z of rho w. This term can be written as divergence of rho v in vector calculus notation. So we are left with the equation this equation. Del rho del t plus del dot rho v equal to 0. This equation is known as continuity equation. Okay. So the continuity equation physically conveys what? It physically conveys the constraint for conservation of mass. The continuity equation can be written in both differential and integral form, and this is a way of writing the continuity equation in a differential form. We will discuss bit more elaborately about the continuity equation, but before that let us try to have another method or alternative derivation of the continuity equation. So alternative derivation alternative derivation of the continuity equation. To understand this derivation, let us draw a box like this. For simplicity, a rectangular box. Let us say this is x axis, this is y axis, and this is z axis. Let us say, let us give some dimensions to these sides of this box. Delta x, delta y, and delta z. Now, to begin with, let us write a physical principle of the conservation of mass applied to this particular control volume. So, to do that, what we can write? Let us say that there is some mass of fluid entering this control volume. There is also some mass of fluid leaving the control volume. What is the net change of mass within the control volume? Increase of mass or decrease of mass, it depends on the difference between what is coming in and what is going out, right? So whatever mass is coming in minus whatever mass is going out is the algebraic increase of mass within the control volume. So let us write this statement in words. So m dot in minus m dot out is equal to rate of change of mass within the control volume, right? So this is the very basic conservation principle in a physical sense. Next, our objective will be to write it in terms of the flow parameters. So m dot in. Now m dot in, let us try to sketch this. So m dot in, now m dot in can be along x, along y, along z, there are different directions. For simplicity, we will analyze what is happening along x direction, and then we will have similar considerations for y direction and z direction. So this is m dot in along x, and this is m dot out along x. So m dot out along x is nothing but m dot at x plus delta x, right? That is the mass flow rate. If this phase is denoted by x, then this phase must be denoted by x plus delta x. Alright. So m dot out is nothing but m dot x plus delta x. So m dot in minus m dot out is nothing but m dot x minus m dot x plus delta x. This along x. Similar terms will be there along y and z. So m dot x minus m dot x plus delta x, how we can write it? So now it becomes a problem of mathematics where our objective is to write a function of x plus delta x in terms of a function of x. This we can do by Taylor series expansion. So we can write m dot at x plus delta x is equal to m dot at x plus plus higher order terms. Okay. So m dot at x minus m dot at x plus delta x is equal to minus del x of m dot x into delta x, and then of course higher order terms. Now what is m dot at x? How can you express the mass flow rate along x? Mass flow rate is the volume flow rate times the density. What is the volume flow rate? Volume flow rate is the normal component of velocity times the cross sectional area. So if you consider all these, then first there is density, then velocity component along x, then the shaded area. What is this shaded area? Delta y into delta z. So we can write this equal to minus del x of rho u into delta x into delta y into delta z. Okay. The other terms will be of higher order, and when we take the limit as delta x, delta y, delta z all tending to 0, the higher order terms will vanish. So we can set the conservation of mass so what I will do is I will just refer to the previous slide where we have this term minus del x of rho u into delta x, delta y, delta z for m dot x minus m dot x plus delta x. So what will be the similar term for y and z? In place of x it will be y, in place of u it will be v for y direction. In z direction, in place of x it will be z, in place of u it will be w. So let us therefore write m dot in minus m dot out. This is equal to minus del x of rho u minus del y of rho v minus del z of rho w into delta x, delta y, delta z. And this is nothing but what is mass within the control volume? What is mass within the control volume? The volume of the control volume times the density. So rho into delta x, delta y, delta z. Remember that in the left hand side we also have the higher order terms. So we should technically write the higher order terms before we take the limit. Before we take the limit, we cannot say that higher order terms will be tending to 0. Now we take the limit as delta x, delta y, delta z, delta t all tending to 0. Question is, why are we taking this limit? Eventually our objective is to derive a differential equation. So to derive a differential equation, remember the physical meaning of a differential equation is that it's an equation that must be valid at a point. To make an equation valid at a point, we have started with a control volume. So we must shrink the size of the control volume in a way that it reduces to a point. That means that we must take the limit as delta x, delta y, delta z, and as well as delta t tending to 0, because we want an instantaneous description. So that brings us back to the equation that we derived in another way, that is del rho del t plus del x of rho u plus del y of rho v plus del z of rho w equal to 0. Okay. So this is another way of deriving the continuity equation. Now there are special cases. Steady flow. Steady flow means fluid properties and flow velocities at a given location doesn't change with time. Therefore, density at a given location does not change with time. So this will be 0. Incompressible flow. We have already derived this divergence of velocity equal to 0. Again, that doesn't mean that rho is a constant, which follows from this equation. Now, let us consider a very special case. One dimensional steady flow. One dimensional steady flow. So which term will be there in one dimensional steady flow? Now, for many one dimensional types of flows, we often use an integral form of the continuity equation instead of writing the differential form. So we will look into that form now. Let us say that you have a volume like this, arbitrary volume, looks like a nozzle or something like that, but not drawn with any specific purpose. Let us consider that you have a steady flow across this volume. So you have del dot rho v. To get the corresponding integral form of this equation, the first step is we integrate this equation over the volume of the fluid. CV means control volume. The control volume is whatever is drawn here, and dV is a small differential volume element. Let us say this is dV, chosen within the control volume. Now we use a very well known theorem in vector calculus, which is known as divergence theorem. So the divergence theorem says that if you have a vector function f, if you have a vector function f and this dA is the area vector. Yesterday we discussed that what do we mean by area vector. Area vector is nothing but the magnitude of the area times the unit vector in the normal, outward normal of the area. So f dot dA is equal to divergence f dV. Any function f should work provided this control surface is a surface that completely bounds this control volume. This is important. If the surface does not completely bound the volume, then you cannot apply this theorem, divergence theorem. Now in fluid mechanics, fortunately that is the definition of a control surface, that a surface that bounds the control volume completely. So that works. So here what is f? This is f. So in place of the divergence of f, we can write that integral of rho v dot eta dA what are the surfaces across which fluid is flowing? Let us say this is a solid boundary and this is a solid boundary. So fluid is flowing across this surface and this surface. Let us say this is surface number 1, this is surface number 2. Okay. So we can evaluate this integral on surface 1 and surface 2. Let us say that this is x direction in which the fluid is flowing. So what is the integral over the surface 1? Integral of rho v is u I, right, because the velocity is along the x direction. So v is equal to ui. What is eta? Minus I, right. This over surface 1 plus, consider surface 2 u is ui and what is eta? Eta is I. This must be 0. So we can write therefore minus integral of rho u dA over surface 1 is plus or is okay, let us first write this with plus and then we will change the sides. Let us consider a special simplified case where rho is a constant. Okay, again a special case of incompressible flow. So let us take an example with rho equal to constant. Rho equal to constant means you have minus integral of u dA over surface 1 plus integral of u dA over surface 2, this equal to 0. By definition in fluid mechanics, the average velocity u average is equal to integral of u dA by integral of dA, which is the area. So integral of u dA is nothing but u average into A. So that means from here it follows that u average into A1 is same as u average into A2. This is like your so called A1 V1 equal to A2 V2. Okay, so this is very important. We often see that if the student is asked that what is continuity equation, he immediately says A1 V1 equal to A2 V2. first important concept that you should convey to your student is under what conditions is this valid. We have started with the general continuity equation and we have simplified it to a special condition. That must be ensured. The second thing is the meaning of V1. When you write A1 V1, V1 is not velocity at a point. V1 is the average velocity over a section. So, depending on the need, one can, for problem solving, one can use the differential form of continuity equation or integral form of the continuity equation for whatever special case, but the special form needs to be carefully used and its meaning of symbols must be carefully described. This is one important note considering this. Okay. Now, we will move further ahead with the continuity equation by describing the continuity equation for a very special case of two-dimensional incompressible flow. So, another special case, and there is a special purpose for representing this special case, we will come to that in a moment. Two-dimensional incompressible flow. Let us write the general form of the continuity equation. We have already derived that for incompressible flow, even from pure kinematic constraints, for incompressible flow, this leads to this one. This was derived from pure kinematic constraints in the lecture delivered by Professor Shom just before this. So, from this equation for two-dimensional flow, which term will be 0? The last term will be 0. So, for two-dimensional incompressible flow, this is for 2D. So, for two-dimensional incompressible flow, this will be your special form of continuity equation. Okay. Now, how many parameters are there in this equation? There are two parameters in this equation, u and v. We are interested to express this equation in terms of a single parameter. So, let us define a parameter psi, which in general is a function of x and y. How we define psi? Define psi such that u is equal to del psi del y and v is equal to minus del psi del x. Again, there is no sanctity on which should be plus and which should be minus. It is entirely up to you, because the objective is to satisfy the continuity equation. You see that if you substitute u equal to del psi del y and v equal to minus del psi del x, it automatically satisfies the continuity equation. If you had defined u equal to minus del psi del y and v equal to del psi del x, that would also have automatically satisfied the continuity equation. So, both are valid definitions. It is just the sign convention that you adopt for yourself. So, different books will have different styles. Some book will define u as del psi del y, some book will define u as minus del psi del y. There is nothing wrong with that, provided the other one has the opposite sign. Okay. So, this psi is known as stream function. So, when is the stream function defined? The stream function is not defined for all cases. The stream function is defined only for two-dimensional incompressible flow, because this parametric form is satisfied only for two-dimensional incompressible flow. Otherwise, this will not satisfy the general continuity equation. So, why we are referring to continuity equation all the time? Because no matter how complex or how simple your velocity field is or your density field is, it must satisfy the continuity equation. Otherwise, it is not a physically valid velocity field or physically valid density field. So, the stream function, now out of so many names, why is it called stream function? Let us try to write the stream function as a function of x and y and write d psi. So, what is d psi? Del psi del x into dx plus del psi del y into dy. What is del psi del x? Del psi del x, let us, this is minus v and del psi del y is u. So, this is minus v dx plus u dy. So, consider a line with psi equal to constant. If you have a line with psi equal to constant, that means you have d psi equal to 0. If psi is constant, d psi must be 0. If d psi is 0, you must have minus v dx plus u dy is equal to 0. That means dx by u is equal to dy by v. So, what is this? This is nothing but equation of a streamline, right? So, along a streamline, the stream function is a constant. That is why the name stream function. But there are subtle distinctions between the applicability of streamline and applicability of stream function. Streamline is defined for all flows. All flows will have streamlines. All flows will have streamlines. But all flows will not have stream function defined. Stream function is defined only for two-dimensional incompressible flow. But streamlines are defined for all possible flows. So, only this analogy exists when both streamlines and stream functions are there in the paradigm. That means you have two-dimensional incompressible flow where stream function is defined, and then the stream function, constant value of the stream function represents a streamline. At the end, the stream function is a mathematical function that parameterizes the continuity equation for two-dimensional incompressible flow. That is its mathematical relevance. But let us try to get a physical relevance of what the stream function wants to convey. So, to do that, let us say that we are having a line element like this, any line element in the flow field, and let us take a small part of that, call it from here to here, call it dl, a line element. This line element subtends an angle theta with the x axis, and this line element has a normal eta. Let us say that width of the line element perpendicular to the plane of the figure is 1, so that the area of the line element, this is a line element at the end, so its length is dl and width is unit to it, so its area is dl into 1. Okay. So, what is the volume flow rate across this line element? that is nothing but V dot eta dl into 1. Now the next is, so let us write the V and eta in terms of its components. So what is V? V is nothing but ui plus Vj. And how do we write eta? So let us draw a vertical line here. So if this angle, so and a horizontal line here just for simplicity. So if this angle is, so this angle must be theta. If this angle is theta, this angle is 90 degree minus theta, because the angle between the normal and the line element is 90 degree. So the unit vector eta can be written in terms of its components. So let us draw a clearer picture here. This is the unit vector eta. It has its x component like this, and it has its y component like this. Okay, and this angle is 90 degree minus theta. So what is this length of this is 1, because it is unit vector. So what is the x component? Cos 90 degree minus theta with a minus sign, because it is along the negative x direction. And y component is sin 90 degree minus theta so minus sin theta I plus cos theta j. So let us find out what is V dot eta dl. So minus u sin theta plus V cos theta dl. Which elaborate figure? Curved boundary, okay. So this is the curved, this is not a curved boundary actually, it is a curved line element. So you have a line like this is dl, okay, and this is its normal direction. So V dot, that is what is required for this one. Now let us write dl has its, so if you consider the dl having components as dx and dy, and this angle as theta, so dl we can write in terms of dx and dy as follows. So dy dl is sin theta and dx dl is cos theta. That you can clearly see from this enlarged figure. This angle is 90 degree. Okay. That means V dot eta dl, in place of dl sin theta you can write dy, so minus u dy plus v dx, dl cos theta is dx. So this equation leads to this. In place of dl sin theta we are writing dy, in place of dl cos theta we are writing dx. So this is equal to u is equal to del psi del y and v is equal to minus del psi del x. Okay. So this is minus del psi del y dy minus del psi del x dx. The plus or minus sign depends on the sign convention, that is not very important. So this is at the end minus d psi. So if you integrate these between 2 points 1 and 2, what is the difference between psi 1 and psi 2 reflect? It represents the integral of these between points 1 and 2, right? That means the difference between stream functions at 2 points represent the volumetric flow rate across that line element between 2 points. So if you have psi 1 and psi 2, the difference between psi 1 and psi 2 will represent the volume flow rate through the curved line element between 1 to 2. Okay. Now test this concept for a case when this curved line is a streamline. If the curved line is a streamline, then what happens? If the curved line is a streamline, then psi 1 is equal to psi 2. That means there is no flow across this curved line, and we know by definition there is no flow across a streamline. Okay. So this is a sort of a physical interpretation of the stream function, that difference between stream functions represents the volumetric flow rate per unit width, of course. The next concept, so we have discussed about the conservation of mass and we have discussed about the stream function and its relation with the conservation of mass. The next concept that we will discuss is the concept of velocity potential. So let us recall one of the important things that was learnt in the morning lecture, that the angular velocity of a was obtained as half of curl of the velocity vector. Physically, what was the angular velocity? So if you had a line element, two line elements that were perpendicular to each other, the average velocity, average rotational velocity of these two line elements. So this is in rotation in one plane. Similarly, there could be rotation in three different planes. So each rotation will have a component, and if you add all the components, this is the compact vector form it will look like. So this is defined as the vorticity vector. So vorticity vector physically represents the rotationality in the flow. So if you have a straight element in the flow, if the flow is rotational or the rotationality is there in a loose sense, we will talk about what is irrotational and what is rotational flow later on, then it will keep its orientation like this. But if there is a rotationality in the flow, its angular orientation will be disturbed. So now for irrotational flow, that means there is no rotation. That means you have curl of the vector, velocity vector is a null vector. Now there is a very well known vector identity that curl of gradient of a scalar function is a null vector. This is a vector identity, an identity derived in the context of vector calculus. That means if curl of the velocity is a null vector, then we can express V as grad phi, where this phi is a scalar function. So V is grad phi. When can we write? We can write only when the flow is irrotational. Now can we write V is equal to minus grad phi? We can still write that, because in place of grad phi, if you substitute minus grad phi here also, that is satisfied. So again, different books write it in a different way. Some books write V equal to grad phi, some books will write V equal to minus grad phi. Both are acceptable. It's just a matter of sign convention that you adopt. So V is equal to grad phi. This definition is valid only if it is an irrotational flow. So if you write its scalar components, that means U is equal to del phi del x, V is equal to del phi del y, and W is equal to del phi del z. Where phi is a function of x, y, z. This is known as velocity potential. Again, to iterate, velocity potential, when is it defined? It is defined for irrotational flow. That irrotational flow may be 2-dimensional, 3-dimensional, whatever. So there is no restriction of 2-dimensionality which was there for the stream function. Now before proceeding further, let us work out a very simple problem to understand that how we can relate the velocity field, stream function, and velocity potential. Let us take an example. Let us say that in consistent units, U equal to x, V is equal to minus y, W equal to 0 in some consistent units. First question, is it a 1-dimensional velocity field, 2-dimensional velocity field, or 3-dimensional velocity field? It is a 2-dimensional velocity field. So first observation is it is 2-dimensional. Second is it a valid velocity field? How will you justify it? You have to see whether it satisfies the continuity equation. In fact, it satisfies the continuity equation for 2-dimensional incompressible flow. So 2D plus incompressible. Because it satisfies the 2-dimensional incompressible flow continuity equation. So del U del x is 1, del V del y is minus 1. The sum total is 0. This is satisfied. Because it is a 2-dimensional and incompressible flow, the stream function is defined. So let us find out what is the stream function. To calculate the stream function, we use the definition u is equal to del psi del y. That is equal to x. So that means if you integrate this partially with respect to y, then what is psi? Psi is equal to xy plus a function of x. Remember, when you are integrating with respect to y partially, function of x is like a constant. So this function of x may include some function of x plus a constant, a general function of x. Similarly, v is equal to minus del psi del y. Sorry, minus del psi del x. So that is equal to minus y. So if you integrate it partially with respect to x, psi is equal to again xy plus some function of y. So if you compare these two, this one and this one, if you compare, then comparison tells that psi is equal to xy maybe plus some constant. Okay. Now let us inquire on the existence of velocity potential. To inquire on the existence of velocity potential, what we must check? We must check whether the flow is irrotational or not. This is a two-dimensional velocity field, that where the flow takes place in the xy plane. So if the flow is taking place in the xy plane, it is good enough for us to check whether the angular velocity with respect to the z axis is 0 or not. So what is this? Half of del v del x minus del u del y. This formula was derived by Professor Shom in the previous lecture. So what is del v del x? This is 0. What is del u del y? See, v is minus y, so del v del x is 0. U is equal to x. Therefore, del u del y is also 0. So this becomes 0. That means it is an irrotational flow. Because it is an irrotational flow, you must have phi defined. So let us find out what is phi. So u is equal to del phi del x, which is equal to x, and v is equal to del phi del y, which is equal to minus y. This is what we all know from the given velocity field. So if you integrate this partially with respect to x, then phi is equal to x square by 2 plus function of y, not c, because this is partial integration with respect to x. when you are integrating with respect to x, function of y is like a constant. Similarly, when you do this, phi is equal to minus y square by 2 plus function of x. Now you compare these two. If you compare these two, what is f3y? f3y is minus y square by 2. And what is f4x? X square by 2. So you can write phi is equal to x square minus y square by 2. You can add a plus c because your choice of this c depends on the choice of the origin of phi. So you can choose a reference phi such that this c becomes 0. So if you choose, for example, that at x equal to 0 and y equal to 0, phi equal to 0, that will lead to c equal to 0. Okay. So this choice of c is arbitrary. It depends on your choice of the reference. So from this example, I believe that we could clarify that how you can relate the velocity field with the stream function and the velocity potential, provided both are defined. Now finally, we will try to discuss a special case when both the stream function and the velocity potential are defined. So special case when both phi and psi are defined. When psi is defined, when is psi defined? Two-dimensional plus incompressible flow. When phi is defined, irrotational flow. So when both phi and psi are defined, 2D incompressible irrotational flow. 2D plus incompressible our next objective will be to relate the constant psi lines and constant phi lines under such special conditions, that whenever you have 2D plus incompressible plus irrotational flow, how are lines of constant phi and lines of constant psi related. So to do that, it is a very simple exercise, it will just take a couple of minutes. Psi is a function of x and y. So what is d psi? Del psi del x is, in terms of uv, what is this? This is v, and del psi del y is minus u, or the other way, u is equal to del psi del y if we write, then v is equal to minus del psi del x. So one has to be minus, the other has to be plus. So that means when you have psi equal to constant, that means d psi equal to 0. That means dy dx, which is the slope of psi equal to constant line, this is v by u, right? Similarly, let us write phi as a function of x and y. So d phi is this. So what is del phi del x? This is u. And what is del phi del y? This is v. So phi equal to constant means d phi equal to 0, which means dy dx for phi equal to constant is equal to minus u by v, right? So let us say, let us make a sketch. Let us say this is a phi equal to constant line, and let us say that the green line is a psi equal to constant line. We want to find out the relationship between these two lines wherever they cut. So what is the meaning of dy dx of a curve at a point? It means the slope of the curve at a point. So let us consider the common point where you will have the point of intersection. So at the point of intersection, you have a tangent to the red line, you have a tangent to the green line. What is the slope of the tangent to the green line? This is the slope of psi equal to constant, that is v by u. What is the slope of the tangent to the red line? That is minus u by v. So m1 is equal to v by u and m2 is equal to minus u by v. So what is m1, m2? m1, m2 is minus 1, right? That means these two tangents are at an angle of 90 degree with each other. So phi equal to constant lines and psi equal to constant lines, they are termed as orthogonal to each other. Orthogonal means they are common. Whenever you have their common point of intersection, tangents to the common point of intersection are perpendicular to each other. So the very important relationship between the constant phi and constant psi lines is that they are orthogonal to each other. One very important caution: there is a point where they are not orthogonal to each other. What is that point? What is that point where psi equal to constant line and phi equal to constant line are not orthogonal to each other? See, when you are writing m1, m2 equal to minus 1, we are cancelling u and v. That means we are assuming that u and v are not 0. Otherwise you cannot cancel u and v, there will be division by 0. So when is u and v 0? U and v are 0 when the velocity field is 0. That is called as a stagnation point. So phi equal to constant and psi equal to constant lines are orthogonal to each other everywhere in the flow field except the stagnation point. This is very important. At the stagnation point, there is no question of their orthogonality. This concept must be clearly brought in. Finally, we will derive, for the case where both phi and psi are defined, we will derive the governing differential equation that describes both phi and psi. So let us say that u is equal to del psi del y, v is equal to minus del psi del x. From where it is derived? Two-dimensional incompressible flow. Two-dimensional incompressible flow, right? If it is irrotational flow, this is 2D plus incompressible. Now we add the constraint of irrotational flow. If we add the constraint of irrotational flow, then you must have del v del x minus del u del y equal to 0. Angular velocity with respect to z axis must be 0. So that means In other words, we can write the Laplacian operator del square psi equal to 0, where the del square is basically del 2 del x2 plus del 2 del y2 plus del 2 del z2. Here the z component is not important because it is a two-dimensional flow field, so this is not important. So del square psi equal to 0, this is the governing equation for psi when it is two-dimensional, incompressible, irrotational. All these three conditions are satisfied. Now let us come to the definition of phi. Irrotational flow u is equal to del phi del x, v is equal to del phi del y. On the top of that, we impose the condition for 2D and incompressible flow. That means it should satisfy the continuity equation del u del x plus del v del y equal to 0. Okay. So you substitute u equal to del phi del x and v equal to del phi del y. This will mean del square phi del x square plus del square phi del y square equal to 0. That means you have del square phi equal to 0. This template equation, Laplacian of a function is equal to 0, is a very important equation in engineering, and this equation, this prototype equation is known as Laplace equation. So when you have both two-dimensional, incompressible and irrotational flow, both stream function and velocity potential satisfy Laplace equation. But that does not mean that their solutions are same, because boundary conditions are different. Their boundary conditions are different, therefore solutions are different, but the governing differential equations are the same. So we can conclude this particular session by stating that what we have learned that various kinematic parameters related to the flow, the conservation of mass, and we have also learned the definition of stream function and velocity potential and important relationships between the velocity potential and the stream function. There will be more elaborate discussion on the velocity potential in one of the lectures by Professor Ghosh Maulik when he will be talking about the potential flows. So let us stop here for the time being. Thank you. Yes.
Sir?
Sir, at stagnation point, the product of M1, M2 is 0.
No, these are not defined, because at the stagnation point, you have V by U and U by V, both are 0 by 0.
Okay.
Therefore, at the stagnation point, these are not defined.
Not yet defined.
Not at all defined.
Sir, what about at singularity
one more
point?
question, sir. What is the physical meaning of the negative sign of phi and psi?
There is no physical meaning of negative or positive sign. The negative or positive sign, one sign opposite to the other comes in the psi definition to make sure that the continuity equation is satisfied.
But
So,
in your explanation you told, sir, psi it may have the negative value.
whatever psi value has, see, it's the difference in psi that matters.
Yes, sir.
The difference in psi value.
Yes, sir.
So let us say that you have one value of psi 10, another value of psi as 20.
Okay.
Okay. Then one value of psi as 0 and another value as minus 10. The difference is still the same.
Okay.
Okay. So the
Sir,
difference is important.
Thank you. Thank you, sir.
Sir, will streamlines and potential lines will be perpendicular to each
Who is
other at
asking this
singularity
question?
point?
Yes.
Will streamline and potential lines will be perpendicular to each other at
You
singularity
cannot,
point?
you should not say perpendicular to each other. That is wrong. Orthogonal to each other. There is a
Sir.
difference between orthogonality and perpendicularity.
Yes, sir. Orthogonal each other at singularity
Except
point?
for stagnation point.
Singularity point?
Huh?
At singularity point?
What is similarity point? Huh?
Singularity.
Singularity point.
Yes.
The stagnation point itself is a point of singularity because there is division by 0. Singularity means division by 0.
Okay. So it won't be.
Okay, if we have more questions, we will take it up in the tutorial session. Thank you.
Next session, there is a one question regarding this
Yes.
total derivative form of continuity equation d rho
Yes.
by dt plus rho divergence of v vector.
Hmm.
So the expansion is not clearly understood in this, like
Yes.
u into d rho by dx plus v into del rho by del x, del y plus so and so other terms.
First of all, you tell me, do you understand what is total derivative? This is the first question that you answered
Yeah.
to me. You understand it? So then capital D dt is del del t
The second term, divergence.
plus u del del x plus v del del y plus w del z del z. That
It's
you
fine.
accept? That
Correct.
is the first term. Second term is there is a divergence of velocity vector. So change in volume per unit time is the divergence of velocity vector. That has been derived.
Exactly.
So divergence of velocity vector is del u del x plus del v del y plus del w del z, and these are
But
just
there is a one more-
algebraically added.
But one more term come here, that u into d rho by dx plus v into d rho by dy.
That is within the total derivative. So that is why I have asked you that have you understood what is total derivative? If you have understood what is total derivative, you will know what is that term. That term is del rho del t plus u del rho del x plus v del rho del y plus w del rho del z. So that term is a part of the total derivative.
And it was told in the first session, you probably have forgot total derivative and the convective derivative.